All right, so let me welcome you once again to another concept on domain. We've already talked about domain of radical functions and rational functions. This time, you are going to get questions which are combined, both rational and radical, okay, in a fraction form. So we are going to look at how we can find the domain of such examples. Okay, so for first one, we are given a function of this form to find the domain. Now let's look at how to find the domain. D subscript what f, that means the domain of the function f is given as what we are saying that x such that x is a member of real numbers. Each at x should be greater than 0. So when you are given such example, all that you need to do is to find values. As we already said in the previous video or lesson, we said that to find the domain of a function, we are looking at the values of x for which the given function is what defined. So whatever value you get at the end of the day, if you substitute the value for x, your function must not be undefined. Okay, we also said that whenever you have a negative value in a radical sign, that makes what the function undefined. So you need to make sure whatever you get, you not get a negative number in the square root or the radical sign. That is what we discussed or we talked about in our previous lesson. This time, let's look at how we can look at it. So if you look at all these forms, you see that each and every one has its own given domain. So when the radical sign is on the function at the numerator, this is how we find the domain. All right, that is how we write the domain. What if the radical sign are on what? We find two radical signs on both the numerator and the denominator. Then this becomes a third. So in that case, you do this separately, you do this separately. The same applies here. But in this case, the first one, you only consider the denominator. But when you have this in the case of example 2 and 3, you need to do it separately. All right. Okay. If that's the case, then let's look at some examples and see how we can go about it. So this is our first example. We'll not waste time on that. Let's see how we can solve that or find the domain of such function. So I will begin with my solution. Great. For example 1, we are seeing that the function f at x is given by x minus 1 all divided by square root of x plus 3. Now, as we said that the domain of such example is that whatever value we have here in the radical sign shouldn't be negative, or whatever here shouldn't be what? Everything for the denominator shouldn't be 0, or there shouldn't be any negative in the radical sign. Other than that, the function is going to be what? Undefined, and we don't want that. If that is the case, then the only way this function can be defined is when we say x plus 3 is greater than 0. Yes, when x plus 3 is greater than 0, then the function can be what? Defined. So let's see. In this is what basic principles of what inequalities. So to find the value of x, I can just subtract 3 from both sides, and that gives me this gives me x should be greater than what? Negative 3. Good. Now this is what we have. Okay. All right. But as we always do, we can't just uh, decide that this is our answer. We need to test. Okay. We need to test. So if I'm testing this, then I will draw my number line, indicate where I have. So this is my center. Now I have my -3 here. Okay, in this case, we are saying that x should be greater than -3. So I'm looking at the direction or the side where all values are greater than -3. Looking at it, always we say that the right side are the positive side, and they are what greater than those at the left side. So if this is 3, then this direction becomes what my positive side, which is the right side, and this direction becomes my negative side. Okay, so we are looking at the values that will make the function what defined. So we are only testing to see if indeed the answer we have gotten is right. So if we are saying that these are uh, x values that are greater than -3, then these are also x values which are less than what -3. So we test them and see. We pick numbers from this region, okay, and then we pick numbers also from this region and test if they are the same. Once we pick number, you realize that if you pick any number, let's say -2 here, if we substitute, you realize that here becomes what 1. If you substitute here, so it will make the function what defined. If you pick any number from the left side, which is numbers less than -2, for instance, if I pick -4 and substitute here, you realize that if I put -4 here, here will be what -1. And remember, we said that radicals and shouldn't take what a negative number. We are not dealing with, as I previously said, that we are not dealing with what imaginary what roots or complex numbers. Okay, so because we are saying that the left side, every number you pick here will make the function undefined, then we are not accepting this portion. So it means that this rather becomes what our solution. Okay, so it means that our answer, we are right. Then we can use that inequality as and write our domain. If that is the case, then what will be my domain? So my domain is going to be x is such that x is a member of real numbers, x is greater than -3. Good, so this is my domain. Now let me write the interval notation as I always give, as I said. So for interval notation, we know that this -3 here, this portion is not included. So once it is included, it means that we cannot close it. Okay, yes, it is not included, so we cannot close it. We only write this, that's -3, and we are saying it's greater than 3, so we are moving to the direction where we have all positive numbers. For that matter, we are getting positive what infinity. Okay, good. So this becomes our domain. All right. Okay, now let's look at the example 2 as well. Okay, all right, great. For example 2 now, we are saying that when you have such example, all that you do is you need to work for the numerator and work for the denominator. So we are going to pick the 2. So for example 2, as I said, this is what you do. So I'm going to do them separately. So we have this plus 1. Now, if we are doing this, then it means that we treat this as what? A radical function. And you know how we do that. And we are also going to treat this as when you are solving what? a rational function. Okay, so it means that for the entire function to be defined, then the numerator where we have x plus 1 should be what, greater or equal to 0, or 2 minus x should be what, 2 minus x should not be equal to 0. Okay, good. So these are the condition that will make the function what, defined. Other than that, the function will be what, undefined. So let's solve these two equations. Then we have x is greater or equal to -1, and then we have here too, if we solve, we are going to have x is not equal to negative, or yes, +2. Good. So these are our solutions. So it means that if you consider the second part, every real number or every number can make the function what, will satisfy, except 2. If you also come here, it means that the only values that can make the function defined is what, numbers that are greater than 1 or equal to -1, or numbers that are greater than -1 or equal to -1. Good. So we are going to test and see whether the two will work. Then we know the domain that we are going to write. So I will draw my number line. I will indicate my what do you call it? I will indicate here as -1. Now I will indicate here as 2. Good. So if I have -1, we are talking about the portion or the region where the values are greater than -1, and I can talk of the right side. So it means that my direction should be here, and we are also saying that for the 2, the +2, every number can satisfy except that. So it means that we don't have to. So when you go to this side, it means that it will satisfy. If you come to this side, every number to the right and to the left of the 2, all of them can satisfy or make the condition or the function defined except that 2. So let me even continue like this. Okay, but we also need to consider, once we have double like this, we need to consider whether, if we are picking all values after the 2 to the left side, if we substitute, because we are saying that for the denominator, when you consider the denominator, every element, whether being at the left side or at the right side, will satisfy the condition except the 2. But we also ask yourself, if I should I pick any number from the left side or the right side of the 2 and substitute here I will get a value. What if I substitute the same value in the x at where we have the numerator? Is it going to substitute? You realize that no. The same way, we are also saying that when you pick values that are greater than or equal to -1, it's going to make the function defined. But we know that 2 is what, greater than -1. So that means if I put 2 here there will be a solution. But what if I put the 2 here? Because the second also saying that it shouldn't be 2. So in this case, all that we do is we consider the values that can work for both this one and this one. Yes, we consider only values that if we substitute it here, it will make the function what, define. The same thing, if we substitute it here, it will make the function define. Those are the regions we are going to consider. So let me say I have 1 here. If I look at my left side, which the 2 is saying that everything at my left side should satisfy. So you ask yourself, if I pick -2 here and substitute it here, you realize that you get -1, which makes this undefined. In that case, it means that all these regions are not part. Okay, now let's also consider this region. After 2, if I pick any value, let's say 3, and substitute it here, is the function going to be defined? Yes. If I put it here, is the function going to be defined? Yes. So it means that after 2, this region is also will satisfy. What about from 1 to 2? Okay, if I pick any number, let's say if I pick 0, or if I pick 1, let me use 1. If I pick 1 and substitute it here, will the function be defined? Yes. If I put 1 here, will the function be defined? Yes. So you can realize that we can start from what? Here. Okay. -1 to 2, except the 2 and then the rest. Then from here to here will satisfy. If that is the case, then I can conclude that this is true except the 2. Okay, so I can just write, therefore my domain is given as x belonging to all set of real numbers. Then x should be greater or equal to -1, or x shouldn't be equal to 2. So in the case of writing the interval notation, now that we have realized that from here, from this portion going, except these 2 here, when I get here, 2 will not satisfy, but from here everything will satisfy. And what about from here? Everything will also satisfy. So my interval notation is going to be, I will open this one because the equal sign, so I will close the 1 like this, which is -1. 2 from here to 2, because the 2 is not part, the 2 is not inclusive, and we are saying it shouldn't. So I will bring open. Open means the 2 is not inclusive. Then I'll bring my union and start from 2, because we are also saying that after the 2, the rest, every element here can also satisfy. Then it means that 2, which is not inclusive, 2, if you go to this direction, the right direction, then you realize that it will be infinity. So I will use my infinity, and that is also what? Open. So this becomes what? My domain. Now when you have such example, that is how we go about it. All right, that's very good. Now let's look at the last part, or the third example. Okay, let's look at the third example. Now in the third example, this one as well, you solve it separately. So you are going to deal with this one, the numerator, which is x plus 1, or the denominator, which is 3 minus x. Good. So for the numerator, for the function to be defined, then the numerator x plus 1 should be greater or equal to 0. Or for the denominator, for the function to be defined, then 3 minus x should be greater than 0. So when you have examples like this, this is how you solve it. You take the numerator, solve it separately, but it should be greater or equal to 0. And you take the denominator, that one should also be what? Greater than 0. If that is the case, then I can have my x to be what? Greater or equal to -1, or I can have my x, to be what? Less than 3. Because if I simplify this, or if I solve this, when this goes there, it will be negative, and then the sign has to what? Change. Good. Now once you have this one, then you also need to test this and see. So you quickly draw your number line, indicate your center. So you have your center, and then you have what? Your -1, and then I have my +3. Good. Now if you look at this portion, we are saying that we have -1 here, which is inclusive. Okay, good. Now we have 3 here, which is not inclusive. So we are saying that 3 should be what greater than x. So we are looking at all values of 3 that are what all values of x that are less than 3. So if that is the case, then I can talk of what 2, 1, 0, -1 up to infinity. And we are also saying that we are looking at what numbers that are greater or equal to -1. If that is the case, I can also talk of what 0. I can even talk about -1 itself because it is inclusive. 0, 2, 3 up to infinity. If that's the case, then we can consider this portion and consider this portion outside these two and see whether they can work. Now, if I want to continue from the 3, we are saying that numbers less than 3. So we can go on like this to infinity. Then I have all these values here. And if I start from 0, we are saying the number should be greater. So I can also continue going and then to what? Infinity. It means that every value I pick here should satisfy this condition. Here to everybody, every number I pick here should also satisfy this condition. But you ask yourself, if I pick every number here for this, does it satisfy this condition? Also, if I pick every number for this one, does it also satisfy this condition? You realize that there are times that, for instance, if I pick a number from here, we are saying that it should be less than 3. Okay, so if I pick -2, -2 is less than what? 3. Let me see if I substitute it here. Okay, if I substitute the -2 here, you realize that it will satisfy it. What about if I substitute it here? You realize that it will not satisfy. So it means that we can't consider this portion. Let me also pick another number here. Let's say 4. If I put 4 here, will it satisfy the condition? No. If I pick it here, yes, but here it will not satisfy. So it means that I will not pick this side as well. Now let's look at the middle from -1 to 3. If I pick -1 and substitute it here, am I going to get an answer? Yes. What about this? Yes, it also satisfies. If I pick 0 and put it here and put it here, does it satisfy? Yes, it satisfies. If I pick, let's say 2 here and put it here, does it satisfy? Yes. What about here? It also satisfies. So it means that the only region that can satisfy is from 1 to 3. If that is the case, then we know that if I want to write this one, here will be what? -1 greater, less or equal to x less than what? 3, because this one is not inclusive, but this one is inclusive. And here will be what? X is less than or greater or equal to what? -1. And here is also x is greater than 3. So it's only this portion that satisfies. Then that becomes my solution. So my solution, which I'm going to use as my domain, is then what? X is such that x is a member of real numbers. -1 is less or equal to x less than what? 3. And that is my domain. For interval notation, since this is inclusive, this is not inclusive, I can close the negative part, which is 1, comma, then it ends here. So I write my 3. The 3 is not inclusive because if I should substitute 3 there, it will make the function undefined. So I will bring open, and that answers everything. So this brings us to the end of the first session of rational and radical functions, the domain. So we end here and continue in our next videos. In our next video, we are going to solve more examples on that. So stay calm and watch our next video. Okay, see you there. Bye bye.